Hey there, I'm Andrew, the Communications Manager of Group 6 of the OGO Energy Challenge project, and I'll be taking you through the introduction of our project. I'll be talking about electric vehicles, the background of our project, our goal, our group approach, and the overall content that follows. So first off, about electric vehicles. Electric vehicles were introduced in around 1870, and as the automotive industry became more and more packed, companies had to find a way to stand out, so they started innovating, and thus led to the production of electric cars. Add to this the fact that CO2 emissions were increasing, and governments were putting regulations on the carbon dioxide emissions. Electric vehicles run on a battery, and this battery powers an electric motor which then drives the wheels. And it can be thought of more of as an energy conversion system where the chemical energy in the battery is transferred into kinetic energy, driving the electric motor, driving the wheels. It's also important to note that full electric vehicles weren't always present. It started off more as a hybrid, which is a combination of the internal combustion energy as well as the battery operation. This leads me on to our project background. So we have EPE and we have EPE vehicles. Now EPE stands for Electromechanics and Power Electronics, and they are our host for this project. EPE Vehicles is a car manufacturing company and the customer of EPE. Now, EPE Vehicles has decided to produce their first electric car, and because this domain is new, the Chief Technical Officer, the CTO, has decided to produce a scaled-down model for testing purposes. Furthermore, the CTO has decided to pair with Eindhoven University of Technology, that's us, to research on the energy efficiency of the car and driving practices. So what is this energy challenge project all about? Well, as the main selling point of our car is the energy efficiency, our project goal is to develop and demonstrate a driving strategy for optimal energy efficiency for the model car. And using this, hopefully with our research, we can provide data to EPE vehicles on ways they can improve the energy efficiency of their car, as well as educate them on good driving practices on the road. Now, as this is a very big project, we have decided to split it up into many departments, with each person having 2 to 3 roles. We feel that this is important because each person will be able to concentrate on those 2 to 3 roles and perform them well. As well, each department will have only 2 to 3 people, and we feel this is important because it maximizes the communication. To keep up to date, we have weekly meetings where we keep updated on progress. We talk about things such as what we've done in the previous week, any problems, we update our goals, and we just discuss ways in which we can discuss ways how we can fulfill this project. And we also do peer reviews. This is a way for each individual to review how well they're doing. So onto the content of this presentation. We start with the tank-to-wheel analysis. We have the communication system, we have the speedometer and LED system, and we have the driving strategy. So the tank-to-wheel analysis is basically the determination of the energy losses of each part of the car, as well as the total loss of all components of the car. To do this, we have broken it down into 3 tests. First, we have the wind tunnel test. This measures the aerodynamic drag force on the car. We have the rolling resistance test, measuring the rolling resistance of the car, and the dynamometer test, which measures the efficiency at each velocity that the car is traveling at. Next, we have the communication system. So on the day, the car will be communicating with tow booths on the road, and it will do this via infrared signals. Next, we have the speedometer and LED bars. The speedometer will give us a feedback on which speed we are going at, and this is important because during the driving strategy, we want to control the most optimum speed that we can function at. The LED bars will give us a visual representation of how far away we are from the optimal speed. And putting everything together, we come up with a driving strategy, a way to drive the car on the day. So this factors in things such as resistive forces, the speed of the car, the most optimal speed, the track layout, as well as how much throttle or brake we are using. So that brings me to the end of the introduction. I'll now pass you on to Emma to talk about the dynamometer.
By the dynamometer, I'm going to tell you something about the setup, experiment 1, 2 and 3, and our calculations and results. The setup. It's not our own car we are testing, but it's a similar model. It's standing stationary and the front wheels are on a roller bench. There's also a battery connected to measure the voltage and the current. The first experiment, we are measuring the burning resistance force with we are measuring this with different velocities, and then the roller bench is rotating at different velocities. In experiment 2, it's a combination of experiment 1 and 3. With this we are also using different speeds. The rolling resistance force, the force of the dynamometer, but that force we got. And the battery power, which is the voltage times the current. And the power of the wheels, which we can calculate its formula of the resistance force and force of the dynamometer, and with the different speeds we've measured. And you can see it here that there is a power of the battery and a power in the wheels. So we get both, two powers. Now in the third experiment, we are calculating the power of the battery. And there's a kind of power loss, which is the auxiliary power, and this is measured when the car is not moving, it's stationary. Now our calculations and results. The power of the motor, it can be calculated by the power of the battery minus the power of the auxiliary. The power of the wheels can be calculated by the resistance force plus the force of the dyno times the velocity. And then with that two we can calculate the power of the motor divided by the power of the wheels. It's the efficiency. And all equations have numbers, and each equation has a different number. Then our results. We made a road load for MATLAB to calculate the powers, and we need velocity. We use this every velocity 3 times, with every time it has a different road load. And we did that, and then we got in MATLAB the results. And with these results, there were a lot of results, more than 100,000. And we took the averages of the results. With all the averages and everything, we measured the road load and the speed. We made this efficiency map, and here is the speed and there's the road load. And as you can see in this area, you can see at speed of 10 km per hour and a road load like 6, something 5, 6. It's the best, so it's the most efficient to drive at 10 km per hour. Now Gerbrand will tell you something about the wind tunnel.
I'll tell you something about the wind tunnel. I will first talk a bit about the setup. Then about which constant we are going to calculate, which we have calculated, and about our results. The setup consists of a swing which is within the wind tunnel. There is a car placed upon the swing, which is our car we will be working with. The swing is connected to the force sensor, which will measure the drag force which the car experiences due to the airflow. The airflow is measured the airflow speed is measured as well, and with those values we can calculate the drag force. The equation for drag force is half times the constant of drag times the frontal area of the car times the density of the air times the speed of the airflow, and this can be rewritten to the constant of drag times the area and is equal to some kind of variables which we will be able to get from the experiment. We will calculate the constant of drag times the area, since they're both constants, and this is in our opinion the most accurate way to determine those constants, because otherwise you have to determine the frontal area by using a picture or something else, and this is due our measurements. For our results we have 4 different setups. Setup 1 consists of a base car with a front and rear wing, floor and wheel covers. Setup 2 consists of a base car with front wing, floor and wheel covers. Setup 3 is just the base car with floor and wheel covers, and setup 4 is only the base car. From this graph you can see that setup 2 has the lowest drag force, and therefore is the setup we are going to use in the end results in the test. And then the rolling resistance will be explained in my time.
So yeah, I'll be telling a bit more about the rolling resistance and the communication systems. I'll first talk about the rolling resistance and how we tested it. So during our testing, we first had to do some preparation. We had to prepare our SD card and then install it. We also thought we had to remove the cockpit ourselves, but it was already removed, so it came in handy. Then we did a few tests. So we did 3 setups. So we did one with the cogwheel attached and no body, one without cogwheel and no body, and one without cogwheel and the body attached. And during the testing we basically just pushed the car around, waited for the program to finish, and then do it again. And then we had the results, we had to get them from the log file, and after each setup change we had to get the results on it. And then afterwards we had to do some calculations. So here you can see the test results. So this is the one with cogwheel and no body. As you can see, we had to push it way harder, and it ends way slower because there's more drag, because the drivetrain is involved as well, or more resistance, sorry. The orange one is the without cogwheel and no body. As you can see, there's some inaccuracies in some of the measurements. We basically did 17 tests, and from each 3 of the setups we took one random test and we used that one. And then the green one is without cogwheel and with the body. As you can see, there's a bit of a difference, but not all that much in the green and the orange line. And then we have the test averages. So for with the cogwheel and without body we did 7 tests in total, sorry. And as you can see, the average the acceleration in meters per second is 0.269. Then we did 5 tests without the cogwheel and with the body attached. One of them we couldn't use because we used to push the car on the LED bar, but now the body was covering that up. And during the initial stages for pushing the car, it changed direction suddenly, and that's also why you can see it's a lot higher than the rest of the measurements we took. So that's why we also don't use it in our calculations. And then we have the 4 final tests. These are the ones with cogwheel and without body, and we will probably be using this average to calculate our rolling resistance, because this is closest to the real setup on the test day. And here you can see our calculations, and we basically neglected air force because we are at such low speeds, and the drag didn't calculate at our speed, so we couldn't use it, and we used some of the higher speeds, but the differentiations were so small that we thought they were neglectable, so that's why we didn't use them. And as rolling resistance coefficient, we were probably using 0.0416. because that's the one of the without the body and with the cockpit attached. Then I'll tell you a bit more about the communication systems. So we first had to make an IR sensor circuit. As you can see, these 3 pins are connected to the Arduino. So we have a 3.3 volt and a ground and an output pin from the IR blaster. Sorry, it's not a blaster, it's an IR sensor. So. And we have a capacitor and a basic resistance. We first made it in the computer on the program, and then we made it and we soldered it to a pin board. Then we have the RFID tag. It's also connected with a 3.3 volt and a ground to the Arduino board, and pin CE and CSM are connected to pin 11 and 10 respectively. And then we have the code. So for the IR code, we first initialize the circuit, so that is initializing and enabling the RF receiver, the RF transmitter, sorry, and the IR sensor. And then we set the power level of the radio to low, and we stop the transmitter for listening so it can write. And then we have an if statement, and that's if the IR sensor receives a signal, it continues to the next one, to the next if statement. That checks whether the value is equal to 1, and then it continues to the right. So it writes on the preset address, which is already defined before the setup. We're within the initializing of the circuit, define everything, and it sends the number 6. And then we prepare the receiver for the signal. We prepare the receiver for the next signal after it's sent, otherwise it will just keep on sending, and we couldn't be measuring the times and how many laps we've traveled already. And now Gerbrand will tell you a bit more about speed and LED system.
The problem here is that we have to drive efficiently, and that is the most efficient speed. But we need to see how we can stay at speed. And for that we are using LED bars to show what according to what speed we are driving at. For this we use a sensor which works with magnets on the cogwheel from the engine, a Smith trigger which makes from variable wave a square wave, for LED bars and Arduino. Then there's the calculation we use in the code for the LED bars. We will calculate velocity with delta t, which is in milliseconds. The velocity will be calculated with distance divided by the time, which is in our case delta t. The cogwheel will turn 180 degrees before it reaches a magnet on the cogwheel to the sensor, because there are 2 magnets on the sensor. And in turn we have determined that if a cogwheel turns 180 degrees, the wheel will turn 60 degrees. And with this we can calculate the distance the wheel travels between every time a magnet passes the sensor. This is 1/6 of the circumference of the wheel, where 0.125 is the diameter of the wheel. And then the speed can be calculated with the distance traveled by the wheel divided by the difference in time in seconds. That's why we divide by 1000 again. And then the code. The loop is here the main code, and the other part here is the attached interrupt, as it is called in Arduino. It is interrupted by every time the magnet passes by the sensor, then pin 50 will be triggered. And then the new velocity will be calculated. And then we will go back to the new loop, otherwise you will stay in the loop, main loop. The velocity is calculated by the end time, for which we will use a function milli_s, which will calculate the amount of milliseconds that has passed since the last time the function has been called. And the delta t will be then the difference between the end time and the start time. And the start time will be 0, so delta t will also be the same as end time. And then with those steps we will just make sure that the car is moving, and if the delta t is larger than a certain amount, it probably ain't moving, and so the speed is 0. And if delta t is equal to 0, then there is a speed we have given to it. And then otherwise there is its speed 0. Then we go back to the main loop after the velocity, and first we print the velocity on the LCD screen on the car. which is useful for when we are doing measurements without driving for ourselves, so we can see the speed in numbers. Then we do a small calculation to calculate the number of LEDs that need to turn on, determined by the velocity of the car. Then we will select the color of the LEDs, and they are also determined by the velocity of the car. And then there will be a code function to turn a certain amount of LEDs on. After that, there will be, at the back of the car we have integrated brake lights. At the front there are headlights. Brake lights will only be on when the velocity is decreasing. And then there will be a delay before the loop starts again, because if every time the LED refreshes there will be a white light, and if you don't put the delay in there, they will just keep on showing white light, because there won't be time to show the red, green or the blue light. The colors we are using are red for totally not efficient, blue is for near efficient speed but not quite there, and green is when you are in the efficient speed area. And then here's the code for putting the LEDs on. First we will determine how many LEDs need to be off using the amount of LEDs that need to be on. So you do a small calculation of 32 LEDs on the bar minus the amount of LEDs that need to be on. Then you turn off the amount of LEDs specified by the amount of LED that needs to be off, which is done by this part of the code, which will just open the LEDs can be seen as an array of 96 values, and every 3 values is one LED. They are the color red, green and blue, and you need to put every value on to 1 or 0 to make sure that the LED is on or off. That will be done here. And for the off, the data pin in the loaded data in array will be 0, because then you will put LED off. And after turning LEDs off, the LEDs need to be on will be turned on, and then data pin will be 1, because then you will turn the LEDs on. And that's how our code works. And then Alex will explain something about the driving strategy.
For the driving strategy, a couple things are important. For the maximum efficiency, we need to know which speed is most efficient for the car. We want to minimize the acceleration and braking, so we can calculate, especially the braking, we can see what's more efficient and what's not efficient. And we want to know at what speed we can take corners, because if we have to brake a lot for corners, then we lose a lot of energy. For the most efficient speed, we're going to use the efficiency map from the dynanometer test. In the dynanometer test, the efficiency map, we can implement the forces that were measured at the wind tunnel test and at the rolling resistance test. If we add these 2 forces together, we can see at what different speeds the efficiency of the car. When we were calculating for the most efficient speed, we looked at adding those forces, and we came at around 5 Newton that the car would be driving around the Forum. At 5 Newton you can see that it's closest to 80, around like 9-10 kilometers per hour. So we say that that's our most efficient speed, and that is also calculated into the speed system. For the acceleration and braking, the acceleration we can't really determine a lot, because we only going like 10 kilometers an hour, and for accelerating this speed is really quickly, so it's not a lot of difference if you do a max acceleration or we accelerate gradually. But we think that we should just accelerate immediately, because then we are driving longer at the most efficient speed. So that would cost less energy than we would go gradually, and we had to brake again or something before we take a corner. But we don't want to brake at all, because when we brake with this particular car, the wheels stop immediately. So we lose a lot of power before we get the wheels turning again. So we're going to use another method to brake, essentially. This method is called coasting. We're not going to press the brake at all, we're just going to let go of the throttle, and the car will decelerate on its own gradually. This will lose a lot less energy, and when we have the best speed to take the corner, we can accelerate again and go to the maximum value of the maximum speed again. But we also did a test for the maximum cornering speed. in this experiment we wanted to find the coefficient of the tires to know when at what speeds we could take the corner, the best speed to take the corner. For this we wanted to find mu. This is the coefficient of friction. For this formula we have the formula of mu equals the speed and squared divided by 2 dg. The d stands for the distance that the car has to travel, and the g is the gravitational constant. For the gravitational constant is 9.81, it's everywhere the same on the planet, and in the Netherlands it is exactly 9.81, at least that's what we're told. For the speed, the maximum speed that we were driving during the test was 2.75 meters per second. That is equivalent of 11 kilometers per hour. But the car was limited to this, so there's an error somewhere that we can't drive faster, so it is not the most accurate test. The distance that was traveled with braking was between 8 and 1.5 meters, or 1.05 meters. With these values we could calculate the mu. From this mu we could take the average, and with this average we could calculate speed for the optimum cornering speed. The formula that was used for this is the optimal speed equals the square root of r, this is the radius of the corner, times mu, what's the coefficient of friction, times the gravitational force, divided by the mass of the car. There are two radiuses of corners in the whole track. One is 7.5 meters and one is 10.5 meters, so we calculated them for both. The optimal speed we display here, that's 2.75 meters per second. The average mu is 0.43. The gravitational force is 117 newtons, and the mass is 11.95 kilograms. When we put all these values into the equation, then we get that the optimal speed for taking these corners is 40 and 47 meters per second. This is really fast, so we can't do this. So we're just going to stick to the optimal speed because these numbers give us that we can just drive around at the optimal speed for the whole track, and the only time we have to brake is for the toll system because we have to wait there for 10 seconds. This is the track. With my subgroup we drew the ideal line that we want to drive with the car. When we start here we hug the inside of the track all the way around until we get to the last two bends. Here we have to start coasting to stop before the line so the toll system can do its thing. We have to start coasting somewhere in this area, but we are not exactly sure, so we have to test this on the challenge day itself to see when we have to start coasting to stop with the least power lost. We can use some of the brakes to stop if we're going too fast, but we would rather not do this. And after we stop we can just accelerate and take the corners and do the lap again. We have to do the lap 5 times and then we just have to stop. And we also calculate the fuel consumption that we were thinking that the car is going to do per lap. This is 804,312 joules per lap. This includes the driving line, the optimal driving speed, the road load forces, the auxiliary power and the coasting. So this should be a really accurate guess, but we're not really sure because we could have messed something up in one of the tests, but we'll find that out on Thursday. And now Andrew will finish this video.
Thank you, Alex. So for the final remarks of this presentation, I'd just like to give a status update. So throughout the past few weeks, our team has been working very hard, and we have completed research on the tank-to-wheel analysis, and we've done tests on the wind tunnel, the rolling resistance, and also the dynamo meter. We also have a functioning communication system and a speedometer and LED bars. For outstanding goals, we still have to do the final report, we have to do our individual abstracts, the peer review, and of course the challenge day itself. So that brings me to the end, and thank you.